looking at probability. Some of this beginning stuff today will be a review from probability in junior high. Okay, can't remember if it was Math 8 or 9 that you talk about probability. Okay, we're obviously going to get into more detail, but today's stuff is fairly straightforward. So remember, probability measures the likelihood of the occurrence of an event. Probability can be expressed as a fraction, a decimal, or a percent. If an event can never happen, then the probability is 0. If an event is certain to happen, then the probability is 1. Probability of any other event will fall between 0 and 1. Okay, so can't have a probability of 1.20 or a negative. Okay, it's always a value between 0 and 1. So some more terminology here. So an experiment, that's an action that has measurable or quantifiable results. So when we're dealing with probability, an example would be rolling a die and recording the number on the top of the face. So basically, what's the probability of rolling a 6? Well, there's 6 sides. There's one side that's a 6, so 1 out of 6. 1/6 is the probability. The outcome, those are the different results that are possible for a trial. So rolling a die will have 6 outcomes. The outcome that you're looking for is the actual, like that's what you're going to look for, but the total number of possible outcomes is how many ways that experiment can happen. So for a die, there's 6 sides. One particular outcome of rolling a die is a 2, another one's a 1, 3, a 4, a 5, or a 6. Sample space, that's the set of all possible outcomes of a particular experiment. Often it's denoted with a capital U, okay? But that's the total number of all possible outcomes. So for rolling a die, there's 6 possible outcomes, and so the sample space is all 6 of those, 1, 2, 3, 4, 5, 6. An event, that's the event that you're looking for, so any collection of possible outcomes of an experiment. So an event would be perhaps rolling a die and getting an even number, or rolling a die and getting a 2. That's, the word event really is what you are looking for as a result in that particular experiment. Frequency of an outcome, that's the number of times that it can occur. Frequency, number of times. We've talked about frequency a lot already. Relative frequency of an outcome, that's the frequency that the outcome expressed as a fraction or percentage of the total number of trials. So if you could get 3 red marbles, that would be the frequency, but then out of however many possible there are, say there's 10 in the bag, so that would be the relative frequency would be 3/10. We don't really do relative frequency too much. Okay, so that's just some terminology. Let me just check here. Okay, so looking at experimental versus theoretical probability. So how do we calculate the probability that when a thumbtack is tossed, it will land point up? The only way to calculate this is through experimentation, because there isn't, it's not cut and dried like a die, right, where all the sides are the same, and it's not weighted, it's a fair die, so you can know the theoretical probability of that, but for a thumbtack, there's the shape of it alone, let alone the weight of different parts of it, how it would land, there's a point on it, that kind of thing. You can't just come up with a theoretical with that one. So you would do an experiment. It says, suppose after 60 tosses, the tack lands point up 39 times. So then we would say the probability, in brackets, of the point up would be 39 out of the 60 total times that you tossed it. So that reduces to 13 out of 20, or as a decimal, 0.65. So when a probability is determined by conducting an experiment, it's called experimental probability. Okay? And so that's equal to the relative frequency. In cases where all the possible outcomes of an experiment are known, and all the outcomes are equally likely, then you can talk about a theoretical probability. So if an experiment has n equally likely outcomes, of which r outcomes are favorable to event A, then the theoretical probability is given here. Okay, so r is the number of outcomes favorable to the event, okay, and is the total number of possible different outcomes that could happen. Okay, so that's r over n. In words, there it is. In notation here, this means the number, so n is number of possible events in A out of the number of possible in U, the whole sample set. Okay, so an example in this case, what is the probability of flipping a head with one toss of a fair coin? Experimental probability, so that would be you do an experiment. You toss a coin 100 times and heads show up 45 times. So the probability as a fraction would be 45 over 100, which reduces to what, 9 over 20? As a decimal, 0.45. As a percent, 45%. Okay? Now, that's one experiment. You tossed it 100 times. That's not the same right now as the theoretical probability. Okay, we're assuming that the coin is a fair coin. It's not weighted on one side more than the other. So as a fraction, it would be 1/2. Okay. Only possible outcomes are heads and tails. Okay, so probability of 1/2. As a decimal, that's 0.5. As a percent, that's 50%. So our experiment was pretty close, but not the same. If we did that experiment over and over again, if I told each one of you to toss a coin 100 times, then if we tallied that for our whole class, it would probably be closer. Maybe it'd be 48%. If we got another class to do it, another one, eventually it would get to be approach that 50% or 0.5 theoretical probability. So the more experiments you do, the closer it will get to the theoretical probability. And that's what it just said here. Every time an experiment is performed, the results may be different. For instance, if a coin was tossed 100 times one time, you could get 57 heads. Another time you get 60. When an experiment is repeated many times, the experimental probability will approach the theoretical probability. Okay. All right, sample spaces. So while some sample spaces can be listed easily, there's an extra S on these. Sample spaces for experiments that involve more than one operation may be more easily represented with a grid or a tree diagram. And there's a couple of good examples in the notes package. We actually copy some pages from a textbook, and it has some examples here. This first example is a little bit weird if you read it. It says, illustrate the possible outcomes for drawing 2 marbles from a box containing a number of red, green, and yellow marbles by using a 2-dimensional grid. List the sample space. So in this case, pretty hard to do it exactly when you're not told how many. So we're going to say 2 bags of marbles, or this is a box, right? 2 boxes. Each box has a red, green, and a yellow. okay? And then we'll talk about choosing 2 marbles from there. Okay, so in a grid, so we want to list horizontally red, green, yellow, and then vertically red, green, yellow, and then basically where they meet. So we would put basically dots here. If you had grid paper, then you would have lines, but basically it joins this into a grid like that. Okay. So you can see why if we didn't know how many of each, then we wouldn't, how would we draw that, right? In terms of drawing 2 though, our sample space, we could still get all the sample spaces correct. It's just the grid would look a little bit different. So we basically want to write out each point here. What is it? So red, 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 green, red, yellow, green, red, green, 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 yellow. So I'm actually just writing them out in the same grid order. Underneath. Okay. So that gives us all the possible 2 marble draws that we could have, where we take 1 from one bag or box and 1 from another. We'll talk about conditional probability next week, where if they're all in one bag and you take out 1 marble, then the probability of choosing the next one, it's going to be out of less marbles, right? There's less in there. So it does change the probability a little bit. Okay, but that would be your sample space. And then way down here, what's the probability at least 1 marble is red? Okay, so that, I'm just going to move it up because there's so much space in there. At least 1 marble is red. So this is both of them. This is 1, 1, 1, 1. Okay. So probability, at least 1 red would be 1, 2, 3, 4, 5 out of 9. Okay. And that's for the case where each box had 1 of each. We need to really change the wording in that question because if I didn't tell you that, you wouldn't be able to really calculate the proper probability because you wouldn't know how many of each type of marble there were. So that's a grid. I don't tend to use a grid diagram that much. I do use a tree diagram, which is the next question. So let's illustrate on a tree diagram the outcomes for tossing a 4-sided die and 2 coins. List the sample space. Okay, so for this one, you want to, a tree diagram will have branches, right? So you can decide if you want to do the 4-sided die to start, okay? It's listed first, so I think I will. So we're assuming in the 4-sided die that each side is labeled 1, 2, 3, 4. So I tend to do my tree diagram vertically. So those are the 4 sides of a 4-sided die. Okay, so the 4-sided die would have to be, think about your science, 4 triangles. All right, and then, so then we toss 1 coin, so we could have heads or tails, and that goes for every side of the die. And then from there, we toss another coin. And just listing heads or tails for each possible one. And sometimes it gets a little bit squishy. But that is a tree diagram to illustrate the outcomes, the sample space. Okay, now listing them, we have to write them out. I'm not going to write all of them out. Basically, you would have, you go through each branch, 1 H H, you'd have 1 H T, so that's that, and you'd have 1 T H, 1 T T, etc. Okay, so in total, really, how many possibilities? There's 4 times 2 is 8, times 2 is 16. You look at how many in each part here. So we're really multiplying together. So you can count them up, 2, 4, 6, 8, 10, 12, 14, 16. Yeah, what it asks you. What is the probability that you roll an even number and 1 H and 1 T? So with a tree diagram, you can actually circle them, right? So an even number and 1 H and 1 T. Those. And then here, this even number would be 1 H and 1 T, and 1 H and 1 T. Okay, so there's 4. So down here, probability of even. And 1 H and 1 T is 4 out of 16, which is 1/4. A lot of times we use fractions for probability in lowest terms. Who needs a little bit more time? Raise your hand on Google Meet. Okay, so complement of an event. So the complement of event A is the event that A does not occur. Okay, so it's kind of like the opposite. So the notation for it is, if we're using event A, then the notation for the complement is A with the little apostrophe, it's a prime symbol, or A with a bar over top. Okay, that means the complement. So here's an example. A die is rolled. If A is the event of rolling a 5, then A prime is the event of rolling a 1, 2, 3, 4, or 6. Basically every other possible outcome in the sample set. That's the complement. So the probability of A rolling a 5 is 1/6. So the complement probability will be 5/6. All right, so the probability of A and the complement have to add to 1. All right, so They have to add to 1, so if you want to find the complement of an event, you could go 1 minus the probability that it'll occur. Okay? So if you know in a game, the probability of winning is 0.26, then the probability of not winning is 1 minus 0.26, which is what? 0.74. Okay? That's the complement. So sometimes we talked about that when we did Venn diagrams way at the beginning of the course. We're going to look at Venn diagrams again next week. But that would be, the complement would be like everything that's outside of the circles in a Venn diagram, but still in that sample set. Okay. All right, then mutually exclusive and non-mutually exclusive events. Again, we kind of talked a little bit about this in Venn diagrams. So what is a mutually exclusive event? They are two events, or two or more events that cannot occur at the same time. So they have no possible outcomes. So if you were doing a Venn diagram, so let's say you had a Venn diagram and you had 3 sets, none of them would overlap. If you have a Venn diagram with 3 sets that overlap, then that's called a non-mutually exclusive. Okay? So think of the word exclusive means it excludes things. So it excludes in each set everything else. So each set alone is by itself, right? So a 6-sided die is rolled. Okay? Probability of rolling a 1 is going to be 1/6. Probability of rolling a 3 is 1/6. But you can't roll a 1 and a 3 at the same time. So they are mutually exclusive events because it cannot happen at the same time. So probability of rolling a 1 or a 3, that's going to be 2 out of 6. Could be a 1, could be a 3, so you have more chances of getting something. You have 2 out of 6, which reduces to 1/3. Okay? So, basically, how do we get to 6? By adding these together. Okay? So we add them together. So if events A and B are mutually exclusive events, then when we find the probability of A or B happening, we are adding the probabilities together. Another symbol, a symbol for the word or, is this U symbol. It's union. And again, we talked about that with Venn diagrams back at the beginning of the year, semester. Okay? So we would just add all the probabilities together because there's nothing counted twice, basically. Okay? Another one, card is randomly selected from a standard deck of 52 cards. What's the probability of drawing a queen or an ace? Well, you can never have a queen that's an ace. So these are mutually exclusive events. So you're going to add those probabilities together. So in a deck, how many queens? There's 4 out of 52. And how many aces? There's 4 out of 52. So that adds to 8 out of 52, which you can reduce. You can reduce these ones too if you want. 4 goes into that twice, into this 14 times. Is that correct? 4 goes into that 13 times. I don't know why I said 14 times. Okay. So there's a question here. Okay, so then non-mutually exclusive, we did a lot of work with that in terms of Venn diagrams with numbers of a certain event happening. We didn't do the probabilities. That's what we're going to do next week. But it's the same process. So 2 or more events that have common outcomes are said to be non-mutually exclusive events. So a card is drawn from a standard deck of cards. So the probability of a queen is, remember we did that, just 4 over 52, which reduces to 1 over 13. Because if you've played cards before, you know there's 4 suits, 13 cards in a suit, 1 queen in each suit, so 1 out of 13. Then hearts, well, a heart is, there's 4 suits, there's, and hearts is one of them. So there's 13 hearts out of 52, which is 1/4. And now we use the word and, because we can have a queen that's a heart. In one card, we can get a queen of hearts, okay? We couldn't get a queen and ace together because they are both the numbers, basically, the value of the card. Now, the heart is the actual suit. So queen and heart. So how many are queens and hearts? Well, there's just one, right? That's a queen of hearts. Now, though, for queen or hearts, think about it. You have a deck of cards. There's 13 hearts. One of those is the queen of hearts. So you only have 3 other queens that you haven't counted. So you really have 13, actually I have it here. Well, you can go in this order, 4 queens. One of these queens is a queen of hearts, so then you only have 12 more. So in total, 16 out of 52. So let's take a look at those numbers. If we look at the ones that have denominator, so not reduced, take a look, they all have 52. How do we get 16 out of that? Well, 4 plus 13 minus 1. So really we're subtracting the overlap. So this would be 2 set Venn diagram. And again, we did questions like this at the beginning of the year. So this would be queen, this would be hearts, and this in here would be the queen of hearts, right? So there's 1 in there, there's 12 out here, and 3 out here. Because 1 plus 3 is 4 for that whole circle. 12 plus 1 is 13 for that whole circle. Okay, so you kind of have to remember unit 1. Well, it sure helps to remember it. All right, so drawing a queen and drawing a heart are not mutually exclusive. Drawing the queen of hearts is a common outcome. So note that probability of queen or heart is not found by just adding them together. We have to subtract that overlap because that queen of hearts is included in here and in here. So we've counted it 1 time too many. So we have to find, basically here, it's equal to probability of a queen plus probability of a heart minus the probability of queen and hearts, which is the intersect symbol, and that really means and. Okay. So here's with words to find or, use or, and, the symbols union and intersection. Now, really, you can use this last formula for mutually exclusive as well, because if A and B are mutually exclusive, then the intersection of them will be 0. There will be nothing that overlaps. So you would end up having 0 in here, right? So subtracting 0 doesn't change anything. So you could actually use that formula for any. And I think that's where, yeah, we're going to stop there because the next thing is compound events, and that's what we're going to do on Tuesday.